Now let's look at several clustering algorithms. The first is k-means algorithm. For k-means algorithm, we should specify k, the number of clusters we want to find out. And each cluster will be represented by the center of the cluster. Then in k-means, center is the centroid of the cluster. The idea of the algorithm is also very simple. So at the beginning, we will randomly pick k points as the centroids of the k clusters. Then for each data point in the dataset, we will assign the data point to the cluster, which is represented by the closest centroid to the data point. So we will choose the closest centroid to the data point and assign the data point to the cluster, which is represented by this centroid. And after all the data points have been assigned, we will recompute the cluster centroids using the current clustering. And the steps 2 and 3 will be repeated until there is no change in the identified clusters between two consecutive steps, or the change between the two consecutive steps are very small, or is very small. Now let's look at an example. At the beginning, we have a number of points in the two-dimensional space, and k is 2, so we will randomly pick 2 points in the space as the centroid. Then we will assign other points to the closest centroid. For example, these light blue ones will be assigned to the left centroid, and these dark blue ones will be assigned to the right centroid. So after one step, these 6 light blue points will be assigned to one cluster, and the 4 dark blue points will be assigned to another cluster. After we determine the clustering at this step, then we will update the cluster centroids. So we will recompute the cluster centroids, and these two represented by these 2 red points. Then for each of the data points, we will reassign the data points to the new updated centroids of the clusters. Then again, we have a new clustering here. And after that, we will again update the cluster centroids, and represented by the 2 red points. And then we will reassign the points to the new updated centroid. But this time, we find that there's no change to the cluster membership after reassignment, so the clustering process stops. This is the pseudocode for k-means algorithm. It's also very easy to understand. Initially, we will randomly initialize k clusters centroids, mu1 to mu_k. Then the clustering process is an iterative process. So at each iteration, we will, for each data point, we will find the cluster, we will find the centroid k, which minimizes the difference between the cluster centroid and the data point. And then we will assign this pointer to the corresponding cluster. And after all the data points have been assigned to the clusters, then we will recalculate the cluster centroids according to the new clustering results. And in effect, this algorithm iteratively minimizes the objective function, which is the sum of the square distances from each point to its cluster centroid. And for this perspective, there is an interesting book chapter called K-means clustering in the famous textbook Pattern Recognition and Machine Learning, which explains the K-clustering algorithm from an optimization perspective. Now, one more example of K-means. Here we will deal with the points in a one-dimensional space, so they are real numbers. So we have 5 objects, 1, 2, and 5, 6, 7. So human beings, it is easier for human beings to identify that 1, 2 belongs to one cluster and 5, 6, 7 belongs to another cluster. Now we want to find 2 clusters, and we will use the numeric difference as the distance. So initially we will randomly select 2 points as the centroid. Suppose we select 5 and 6 as the centroid. Now at the first iteration, we will, for each data point, we will find the closest centroid to the data point. So obviously 1, 2, and 5 are closer to the centroid of 5, and 6 and 7 are closer to the centroid 6. So we have 2 clusters, 1, 2, 5, and 6, 7. Now using this clustering, temporary clustering, we will recalculate the centroid. The centroid for the first cluster is mu1, which is 1 plus 2 plus 5 divided by 3, that is 8 over 3, 2.67. Okay, it is about 2.67. And the second centroid, the centroid of the second cluster is 6 plus 7 divided by 2, which is 13 divided by 2 and 6.5. Okay, now we will represent the 2 clusters using the 2 centroids. Now at the next iteration, we will reassign the 5 objects 1, 2, 5, 6, 7 to the nearest centroids. So we can see that 1 and 2 are closer to the first centroid, and 5, 6, 7 are closer to the second centroid. So this is our new clustering of these data objects. And after that, we recalculate the centroid, and in this result, then using these new centroids, we will reassign the objects, and we find that 1 and 2 are closer to this centroid, and 5, 6, 7 are closer to the second centroid. Then the new clustering will be 1, 2, and 5, 6, 7, and we find that this new clustering result is the same as the clustering result in the previous iteration. So there's no change in the clustering membership. Now our K-means algorithm converges to the final solution, and the algorithm stops. And after that, we can measure how good the clustering is. So we will calculate the aggregate dissimilarity measure or distance measure. So the aggregate dissimilarity measure is the sum of the squared distances between each point in all cluster and its cluster center. So here we have 5 points. So we have 5 points. For the first point, the point 5 is 1, and the distance between the centroid of the cluster is 1 minus 5, and we will take the square of this distance. And for example, for the last one, the centroid is 6 and the point is 7, so it is 7 minus 6 raised to the power of 2. Now we add all these distances between each point and its corresponding cluster centroid, and the final result, 2.5, is the aggregate dissimilarity measure, which measures how good the clustering is. If there is a different cluster membership or different clustering, then we can compare the two clustering using this metric. Now the problems of k-means. The first one is we needed to specify k in advance. So we don't know what is the best value for k. So we may need to try different values of k and then calculate the aggregate dissimilarity measure of the clusterings using different k's and find the best k value. And also k-means may tend to converge to a local minimum. That depends on the selection of the starting centroids. So the solution is to run the algorithm for several times and take the best one. Then k-means assumes clusters are spheral in vector space mu2, so it is sensitive to coordinate change. What does this mean by spheral? If you take a look at model-based clustering and k-means clustering, you can find that k-means clustering has some relationship between model-based clustering with the Gaussian, with the assumption of Gaussian distribution. So this is what spheral means. And also k-means is sensitive to outliers. So an outlier is an object with an extremely large value that may substantially distort the distribution of the data belonging to the cluster, which greatly affects the centroid, the position of the centroid of a cluster. Now let's have a look. Let's have a look at an example. So suppose we have a number of points scattered in the two-dimensional space in this way. Now, if we have these 10 data points scattered in the two-dimensional space, it's easy to see that we have two clusters. This is the first cluster, this is the second cluster. But suppose, again, now suppose we have an outlier which is very far from all the other data points. Now what will happen to the k-means algorithm? So suppose we randomly pick a 2 points as the centroids of the initial cluster. So suppose we pick this point and this point. Now, after the first iteration, we can find that these 5 points will belong to the same cluster, and these 5 points will also belong to the same cluster. But because the outlier is also closer to the right centroid, so the outlier will be also assigned to the second cluster. Now we will calculate the centroid, the new centroid of the clustering after the first iteration. Okay, the centroid is here, for example, and for the second cluster, the centroid will be somewhere here due to the impact of the outlier. Now, using the new centroid, we will reassign the points into to the new centroid. So we will reassign the points into to the new centroid. So at iteration 2, we can find that, okay, this point is closer to the left centroid, so this point will be assigned to the left centroid. And similarly, this point and this point will also be assigned to the left centroid. So after second iteration, the left 8 points will belong to the first cluster, and the right 3 points, including the outlier, will belong to the second cluster. Now this violates our intuition because we can see that the 5 points in the middle of the space actually should belong to the same cluster. So this example signifies the impact of the outlier on k-means clustering if we take centroid as the representative of the cluster center. Now there are also some variants of k-means. For example, we can recompute the centroids after every change rather than after all the data points are reassigned. This improves the convergence speed. And we can also think about variants concerning starting centroids. The starting centroids may determine to converge to a local minimum. So we may use some heuristics to pick the good starting points, or we may run k-means several times and pick the best clustering result. Now, we just talked about the outlier problem. This outlier problem can be handled by k-medoid, or the so-called neighborhood-based algorithm. In k-medoid, we will use the medoid instead of the centroid to represent the center of the cluster. This is called partitioning around medoid. So here, in this example, the green points are the medoid, which are real data samples in the dataset. Now, the basic idea of partitioning around the medoid algorithm is similar to the k-means. The difference lies in the step of updating the medoids after assigning each point to the cluster. So the difference lies here, and we will not go into the details. But the basic idea is very similar. Now for the second type of clustering algorithm is hierarchical clustering. In hierarchical clustering, we will create a nested sequence of clusters represented by a diagram, which is called dendrogram. This is a tree-like structure that shows how different objects are grouped together into small clusters, and the smaller clusters are grouped further into larger clusters. And finally, we form such a tree structure where the root node of the tree contains all the data objects. And there are two main types of hierarchical clustering algorithm. The first one is divisive, which starts from the dataset of all objects and iteratively divide the clusters into two until we meet the stop criteria. For example, we meet the predefined number of k clusters. So this is a top-down method. Divisive clustering is a top-down method. But a more popular one is agglomerative clustering, which starts with each data point. So we will put each data point into a single data cluster and iteratively merge the closest clusters into one and the closest clusters into one, and we will further merge the closest clusters into one, for example. So in this way, we do the clustering from smaller clusters to clusters of larger size, that is in a bottom-up fashion. And this algorithm will only stop when we put all the clusters into a single one, which contains all the data objects in the data set. Now let's look at an example of the hierarchical clustering. So at the beginning, we have 6 data sets, and these 6 data points will be assigned to 6 small clusters. Each cluster contains only 1 point. From figure A to figure B, there are two steps. In the first step, we find that A and B is the closest pair, and we will merge this pair into cluster. So we will give it a name called cluster 1.1. And then we find that point C, or cluster C and D, are closest pair, is a closest pair, and we will be merge it into a cluster. We will name it as 1.2. Now we have 4 clusters: 1.1, 1.2, E, and F. And in this figure, in this configuration, we find that we will represent the 2 small clusters with the centroid as the red triangle shows. And then we find that the cluster E and the cluster 1.2 is the closest pair and will be merged into another one. I will name it as cluster 2.1. So this is 2.1, this is cluster 1.1, and this is cluster F. Then we find that, okay, we will recalculate the centroid of the cluster 2.1, and we find that cluster 1.1 and 2.1 are closer, so they will be merged into another one. So I will call it cluster 3.1. And finally, 3.1 and F will be merged into a single cluster. Then the hierarchical clustering algorithm, actually the agglomerative clustering algorithm, stops. Now, a summary: in hierarchical agglomerative clustering, we will start by putting every data point, usually in some data mining literature, they use the word pattern, but actually it is just a data point. So we will put every data point in its own cluster. So initially we will have n points in n clusters. Then we will iteratively find the most mergeable pair of clusters and merge them. Now let's look at another example of hierarchical agglomerative clustering using the one-dimensional example. So again, we will use the numeric difference as the distance between objects. So first, all the 5 numbers are put in individual clusters. Then we will find the 2 closest objects and merge them. So at the first step, we find that 1 and 2 is the closest pair. So we will merge this pair into a cluster, and this cluster is represented by the centroid, and the centroid is 1.5. So now we have 4 clusters. This is the merged cluster one represented by the centroid, and these are the single data centroid clusters. Now we find that, okay, 5 and 6 is the closest pair, so 5 and 6 will be merged into a cluster and represented by the centroid, which is 5.5. And after that, 5.5 and 7 are closer, so they will put together. Now we will represent the final clustering result in this way. So this means 1.2 will be merged first, and then 5.6 will be merged. After that, the cluster of 5 and 6 and 7 will be merged. Then finally, they will be put into a single cluster with all the data points. Now the last question is how to measure the distance between 2 clusters. Actually, we talked about this before. We mentioned the centroid distance measured by the centroids of the 2 clusters, and also the minimum distance between 2 clusters. So in the previous examples, we always represent clusters using the centroid. So we will calculate the distance between 2 clusters by the distance between the centroid of the two clusters. So this is called the centroid link. And we also mentioned that we can also calculate the minimum distance between all pairs of data points drawn from the two clusters. This is called single link. Another alternative is a complete link, which is the maximum instead of the minimum distance of all pairs of points between the two clusters. And also the last alternative is average link, which is the average distance between the points drawn from the two clusters. Okay, finally, some words about the divisive clustering, hierarchical divisive clustering. In hierarchical divisive clustering, we do the clustering in a top-down approach. So at every step, we will choose a cluster to divide. So at the beginning, we have one cluster. Okay, we will divide this cluster. And then if the cluster is divided into two smaller ones, then we need to choose which cluster should be divided further. So the first question is which cluster to divide. Then we will choose the cluster with the maximum intra-cluster distance. Let's recall that we defined this before in the lecture. We will choose the cluster with the maximum intra-cluster distance to divide. But the second question is how to divide a cluster. Then typically we will use some other more easier clustering algorithms like k-means or k-medoids to divide a cluster. So we cannot use a hierarchical divisive clustering to divide a cluster when this is a step of the hierarchical divisive clustering. So in hierarchical divisive clustering, usually we will choose a different clustering algorithm to divide a cluster, an easier one such as k-means. And the hierarchical divisive clustering can stop faster than hierarchical agglomerative clustering because usually the number of cluster k is relatively small. So hierarchical divisive clustering can reach the predefined k value more quickly than agglomerative clustering.